right, what I'm going to do now is we're going to continue on with our discussion of an overview of Java. By the time we get done with all this stuff, which will hopefully be at the by Wednesday, you'll be prepared to do all the assignments we're going to be doing, and then we can start talking about much more interesting topics than Java. So the next thing we're going to talk about are some of the elements that you can have within a class. Some of this stuff should probably be reviewed. There's basically 5 main kinds of things that can go into classes. I'm going to give you a real quick synopsis of those 5 things, and then we'll go through them in more detail. So one thing you can have in a class is something that's called a field. If this was C++, we'd call it a data member. And it's basically a variable that's defined in the context of the class. It goes inside of the class scope. And you can have 2 different types of fields. One are called instance variables. And those are variables where each object has its own copy of the field. So an instance variable is a copy. So for example, here you can see that we have class vector, which we're using as sort of a running example for a lot of this stuff. It has an array of objects, and it has an int that's a count of the number of objects in the array. That's the current number of objects in the array. And those are both things that are part of every object. Every object has its own unique m data, has its own unique m count. Conversely, there's also something called a class variable, which are static. Static has a lot of different meanings in Java, just like it does in C and C++. In this context, static means that there's only one instance of this particular variable for all the different objects. So there's only one of them. That's what static means in this case. It's called a class variable. It's associated with the class, not with the instance. And we'll talk more about that later. We'll also talk about what final means and how you initialize these things. The next kind of thing that can appear in a class are things called methods. Surprise, surprise, that's really the workhorse in an object-oriented environment. And it's basically a set of code that does something. It has a name. You give it a name like element at or index of or size or whatever. And it has a name, and it does some computation, and then it returns a value, potentially. It may not, but it can potentially return a value. You can typically call a method at any point in a program as long as you have access to it. And we'll talk more about access later. And you call it by using its name, so it's pretty straightforward. There are special types of methods called constructors. And constructors are basically the same name as the class, and they're used to create the instances of the class. So they're basically the cookie cutters that are used to initialize the objects. And they look basically like methods, except they don't have a return value. There's also the last type of thing we're going to talk about here are nested classes. And there's a bunch of different types of nested classes. So a class, a nested class, as the name implies, is something that appears within another class. And we'll see when we get a little bit further into this that there are what are called inner classes, which are non-static, and then there's static nested classes. And they have slightly different properties in terms of their dependencies and their relationships with each other and so on and so forth, and the containment relationships that they have. And you'll use a lot of this kind of stuff. In fact, the grad student version of the first assignment implements a nested inner class called iterator, and the grad student version will, in the second version, will do some other stuff, and the undergrads will also implement an iterator as well. Classes can be defined as abstract. You'll see that later when we talk about methods, methods can also be defined as abstract. But basically, an abstract class is a class that cannot be instantiated. It exists solely to define a set of fields or methods that can be used by subclasses. And we'll talk about a bunch of different examples. So here's an example where we have an abstract class called abstract map, which we'll see more about later. And basically, an abstract map can then be used as a superclass for some other class, like, say, hash map. So in this particular case, we can't make an instance of an abstract map. If you were trying to say a new abstract map, that would fail. But we can define an abstract map and initialize it to a concrete type. Now, a concrete class, as opposed to an abstract class, may not have any abstract methods that have not been defined. So it can inherit abstract methods and override them, but it can't define any other on its own accord. Most or all the classes we're going to use for what we do will ultimately be concrete classes, but many times they inherit from abstract classes. We'll talk more a little bit later on about abstract classes. We'll compare and contrast abstract classes with interfaces, And it's probably a good idea to know what an abstract class is and how to compare and contrast it with an interface, because that is likely to show up as a quiz question on the next quiz. So let's talk in a little bit more detail about each of these different elements. So first we'll talk about fields. A class can have one or more fields, actually it can have 0 fields, but it can have one or more fields, and it's used to represent the so-called state of the class. That's basically the values it has. So if you were to have a class that implemented a vector, then the state, the fields, would be things like the array that held the elements and maybe a size that kept track of the current number of elements that were in use within the vector. Fields are often placed before the method declarations in Java. They don't have to be, but it's common practice to put fields in front of the other stuff. So usually you'll say class, foo, or class vector, and then you'll have the fields that come next. Not quite sure why that tradition has grown up, but that's just kind of the way things are done. Fields can be marked with various modifiers to control access to them. And the most common modifiers are private, protected, and public. Now, a public field is one that can be accessed by anyone. As a general rule of thumb, to be violated on occasion, it's usually not a very good idea to make fields public. Does anybody know why that is? What's the downside with making fields public? Why would you not want to do that in a language? What's that? Encapsulation, right. So, and why is encapsulation important?
Basically, prevents information hiding.
So, information hiding.
So if you change the name of the field, it doesn't make everyone else's code obsolete. They were using it and telling it directly.
Great. So you guys hit upon the key points. So the reason we want to typically hide the state representation, hide the fields, is because those usually connote implementation details. And as a good practice in defining systems, we don't want to have the client code, using the word client here loosely, it just means the user of some class. We don't want the user of the class to have dependencies on the implementation details. We want the clients to only be able to access the state via methods. And so if you expose the names of the methods, you're giving their name, you're giving their type, you're giving the data structure representation. If you recall, in CS201, we have different ways of implementing things like stacks, or queues, or maps, or trees. And we don't want to have the client code become dependent on any particular representation. So hiding this information, making it encapsulated, those are all good things. And that's why we typically don't want fields to be public. A protected field can be accessed within the class or by subclasses, but not by clients, not by direct clients of the class, only by subclasses. And then, of course, private fields can't be accessed by anybody except members of the class, methods, and so on. You can assign fields various ways. If you have a field, like let's say we have a class like observable, which is part of Java util, we might have an observable which has a vector of observers. And one way to assign this thing, which is actually what observable does, is it initializes the vector in the definition of the field itself. Pretty typical thing to do, especially if there's only one way to implement this stuff and it's not parameterized. Another way to do it is to defer initializing it and then initialize it in a constructor or some other method. It's usually not a good idea to not initialize it at all, although Java gives default values for everything. But you want to typically have these things initialized. And so one thing to do is put it in the constructor. One thing to do is to have it initialized in the class definition itself. I just showed it here just to show it. But as a general rule of thumb, if there's no parameters that are going to modify the way in which this field is created, you might as well define it when you define the field as opposed to putting it in the constructor, because it's easier to tell at a glance what its value is going to be. You can also refer to the object for which a method or constructor is invoked by using this. So in some cases, it's overkill to do that. Like here's a case where we don't have to say this. We can just say, we could have just left that off altogether. We didn't have to say this dot. Down here, however, notice how the name of the parameter is the same as the name of the field. And so as a result, in this particular case, we have to qualify OBS with this dot so it can disambiguate which one is intended. There's other qualifiers you can give to fields as well. And we'll see a lot of the same things you can do with fields you can also do with methods, so it'll be a little recap later. There's three main things you can qualify them as. Some of them we're not going to talk a lot about now, but others we will talk about later. One thing you can qualify them with is final. Now, if you have a field that's defined as final, that means it can only be initialized once. And you can either initialize it via an initializer, so when you define it, you can initialize it, or you can initialize it in the constructor. But if something's defined as final, you can't reinitialize it anywhere else. So you can think of final as kind of like a constant or a const. It's basically the idea. It's set one time. We'll see that final gets used in other places as well in Java for various purposes. Yes?
If you define it in the constructor and you construct two of them, wouldn't that be initialized twice? Or does
Yes, it would yell at you and wouldn't let you do that. You can also have static. Static basically says there's only one instance of the class. That's the class variable we talked about. Yes, sir?
For final variables, will a subclass be able to reinitialize the final variable?
No. So a static basically says this is one and only one, and so every class can access this one and only one thing. And then the final thing is something called volatile. I'm not going to talk much about that right now. We'll cover this later in the course. Volatile basically means that if you have a concurrent program, namely a program that has more than one thread, a volatile variable can be atomically read to, or read from, and written to atomically without having to worry about inconsistent values. And that turns out to be very important in multi-threaded machines, especially, or multi-threaded environments, especially ones with multi-core, because of the way that caches work. So basically, when something's defined as volatile, it means do not pass go, do not go through some cache, go directly to where the object or variable is stored in memory and write to it directly. We'll talk more about that later. It's not important right now. You can also reference fields various ways. You can reference them by name from within a class. So here's a clone method within vector, and you can see we're accessing its data member called mdata. And then you can also use the dot notation if the field is accessible via a different object. So here's a case where we're going to clone an object to make a local variable, and then we're going to go ahead and access it by dot notation. All right, so those are fields. That should be a review. If you're confused about anything, I'm more than happy to talk about it in more detail, but this should be pretty straightforward. This is more or less the way C++ works with a few little quirks. So if there are no more questions, I'll move on to methods. Yes, sir?
Does Java have something similar to the struct in C++?
No, there are no structs in Java. So the closest thing you could get to a struct in Java would be to have a class where everything was public. So struct in C++ is kind of a vestige left over from C. And so if they had designed C++ from the ground up, they probably wouldn't have had structs. The only difference between a struct and a class in C++ is that a struct has all of its fields and members public, whereas a class, by default, has everything private. So that's the only real difference. Let's talk about methods. So again, you can have one or more, or zero. You don't have to have methods at all. But if you have methods, you can have one or more of them to implement the behavior of the class. And of course, it hopefully goes without saying that the way in which you put the methods in the class ought to be cohesive, right? So the methods that go into a class should have some reason for being put together. Like if you have a vector abstraction, the methods deal with vectors. If you have a stack abstraction, the methods deal with stacks. So what that's called is high cohesion. They belong together for some reason. They can have up to 6 parts. By the way, I saw this movie last weekend. Very cool if you haven't seen it yet. Here are the different parts. They can have modifiers, just like data members can. You can have public and private methods, which have the basic meaning that you'd expect. You can also have package private methods. And you can actually have package private data too, but you should typically have private data as a good rule of thumb. So something that doesn't have any modifier at all, if it just has the name just has the signature of the method, that's what's called package private. And package private means that any class within the same package can access this method, but it can't be accessed by anybody outside of the package. So it's just another form of visibility. I find it a little sloppy to use package private. Usually things become package private when you forget you have to mark something as public, private, or protected. And so sort of by default it becomes package private. But it's usually an indication you just got sloppy. Yeah?
Is the default for fields private?
No, it's package private. If you leave things off, the defaults are package private. You can also define methods as abstract. Now, it doesn't really make sense to have an abstract method unless you also have an abstract class, but you can have a mixture of abstract and non-abstract methods within an abstract class. So for example, here's our abstract map class that we'll see more about as we go along. And you can see that one method called put is not abstract. So it can actually do something, although its implementation throws an exception. And here's another method called entry set, and that's abstract. And so what this says is that anybody who inherits from abstract map has got to provide an implementation of entry set. And the entry set is basically the set of what the map is containing. So it's the key value pairs. It's a tuple. It's a set of key value tuples. So everybody has to provide that. Put does not have to be overridden. If you have a read-only map, you don't have to override put. But if you call it, it'll throw an exception. So an abstract method does not actually have an implementation. We'll show a bunch of examples of this stuff later. This becomes very important when we start talking about dynamic binding. Yes?
So even though that's not abstract, you still can't call it?
Well, whenever you have an abstract method, it's part of an abstract class.
No, sorry. You can't call put even though it's not an
Oh, you can call put. Yeah.
Oh, okay. Wait, so what happens if your abstract class has all like implemented methods?
If the abstract class has all implemented methods, you have to wonder what the people were thinking when they developed it. But it's perfectly legal to do that. It may not make any sense, but it's perfectly legal to do that.
Where do you implement package? Like how do you define it?
Oh, well, I think we talked about, if we haven't talked about packages, we'll talk about them in just a second. But basically, the package is the very first thing that goes at the top of the file. It indicates what package. I think we'll talk about that in just a second. OK. So the return type that tells what the type is. Now, as you can see here, this method, element data, returns type E, which is the parameter of the vector. And set also returns an E. But add element and grow return void. So return void is almost an oxymoron. It just says it doesn't return anything. So it's just a procedure, not a function. There's no value that comes back. You, of course, have the method name. You have a parameter list that goes in parentheses. And it's basically a comma delimited list of input parameters. So you can see we can have more than one. We'll also see we can have 0. They're preceded by their data types. And they're also enclosed. Whoops. And they're enclosed by their parameters. Let's see. All right. This is just low-level syntax stuff, but you have to understand it. So in Java, C++, and C, the data type goes first, and then everything is put around in parentheses. If there are no parameters at all, you still have to use empty parentheses. Another one of those carpal tunnel syndromes, but I won't pay for those. That was the inventors of Java who put that there. There's also something that we'll talk about later. We might get to this today if we're lucky, called exceptions. And you can specify the list of exceptions a method can throw. Does anybody remember? Have you guys learned about exceptions? What's an exception? We'll talk more about them a little bit, but does anybody remember? Yeah.
File not found.
What?
File not found exception.
So file not found is an example of an exception. But what is an exception? I mean, what in general? What's an exception?
Something that's kind of anomalous, stops execution if it's not like caught or whatever.
Right. So an exception is a condition that was not expected, and it typically indicates something's gone wrong. It's some kind of error or anomaly. And Java has nice support for exception handling. And the reason that they have nice support for exception handling is because it makes it next to impossible, without a lot of effort, to ignore exceptions. You can ignore them, but they're hard to ignore. And so they're put in there so that you can separate out the normal flow of control from the anomalous or error flow of control. And we'll see a lot more examples of these. There's different kinds of exceptions in Java. This is an example of something called a checked exception. And that says that this method write object will throw the Java IO exception, or could throw the Java IO exception, and you'd better be prepared to handle it somehow. So you can't ignore it, which actually gets annoying at times. And then, of course, the real interesting stuff is everything between the curly braces. That's the body of the method. Now, like data, or fields, you can have different qualifiers on the various methods. So you can have final, you can have static. So final basically says cannot be overridden or hidden by subclasses. So here's an example of the iterator that's defined in the vector, and it has a method called check for co-modification, where co stands for concurrent, and it basically is checking to see whether or not something's been modified concurrently, and if it has, then things go awry. And we don't want to make it possible to override this. So this is the one and only implementation of check for co-modification. End of story. There's also static methods. Static methods are class methods as opposed to instance methods in a sense. And they can be invoked without having an object. You can invoke them with only the name of the class. Or if you're in the class, you can just call them directly. So here's an example that you'll probably play around with in the arrays helper class that comes with Java that we're using for some stuff for this assignment, assignment 1. And you can see that parallel sort, equals, and fill are all examples of static methods. And as a result, we can say arrays.sort and give it some array. And we don't actually have to have an instance of the arrays class. We can just call the method directly. So that's about the closest thing you're going to get in Java to a good old-fashioned function call in a procedural language like Pascal or more like C. There's some restrictions on what static methods can access. They can only access static fields or parameters. So here's an example where if you were to look inside the arrays class, you'd find they have something called min array sort granularity. I should probably colorize that a little better to make it consistent. So we've got min array sort granularity, and that is a static method, or static data member. And inside the parallel sort method, which is a static method, it can only access parameters or static data members or fields. So you can't access non-statics because it doesn't have an object. Yes, sir?
Can you pass parameters by like reference or cost reference?
So great questions. The question is, in Java, can you pass things by reference and const reference? No. Well, not really. So it depends on whether they're built-in types or user-defined types. Built-in types in Java get passed by value. So if you have something that takes an int and you pass an int, it'll be a copy of the int. User-defined types like vector or stack or whatever, those get passed by, the references get passed by value, but they reference the object. So any changes that you make will go back and modify the object that they're referencing. So one of the questions that sometimes arises with Java is, what if I want to have a function or method that's going to change its parameters that happen to be references? Right? Let's say I want to have some kind of a factory method that's going to modify and create a set of object references for you. How do you do that? And the only way you can do it in Java, because they don't really have the concept of reference parameters the way they do in C++, is you have to create an array of said references, and then you can pass those things in, and the array doesn't get modified, but the array elements can be modified. And so there's a bunch of kind of idioms you have to do in Java to work around the fact that they don't have the concept of const ref and so on. As a general rule of thumb, it is less complicated in Java than in C to deal with these issues. But there are times when you have to kind of stand on your head to deal with the fact that it doesn't have the concept of parameter passing modes with quite the same degree of sophistication that C++ does. And C++ doesn't even really have that sophisticated a notion. Languages like Ada, for example, go much further than that. All right, so that's an overview of methods. Next thing, we'll blaze through constructors. There's not a whole lot to say here. A constructor basically is a method that is specially intended for one and one only purpose, and that's to initialize instances of the class when they're created. So here's an example where we have some constructors. They have the same names as the class that they're defined inside of. And they're automatically called to initialize the instance of the class when you use them with the new operator. So here's an example where we're going to say, new vector, and that'll go ahead and call this guy. So when you say new vector without any parameters, it calls this particular one. And notice, we'll talk about this in a second, you can also, of course, pass in parameters, in which case this vector will get called. So you can see here that they support overloading of method signatures and constructor signatures in Java, just like they do in C++. Although there's no concept of default parameters to methods or constructors. Vectors can also invoke each other. So here's a case where this vector turns around and calls this vector. So you just say this and you give the parameters, and then it goes ahead and calls the appropriate vector. C++ 11 and beyond now have support for something very similar to this. Constructors can call each other. Earlier versions, you couldn't. All right, so that's constructors. They're fairly simple. Let's talk now about nested classes. So classes can be defined within enclosing classes. And you can see here we have a couple of examples in our vector that we're using as the running example. And we'll see here that we actually have two different classes of nested classes, or two different types of nested classes. So one type of nested class is called an inner class. And inner classes can reference non-static instance methods and fields. It can also reference statics too, but it can reference things that are non-static. So here's an example from the vector. So remember, vector has an element count. And here is a nested inner class that's called iter, which implements the iterator interface, and you'll get more practice with that later. And one of the methods inside of iterator is hasNext. And you can see here the way this works, and actually for those of you doing the grad version of the assignment, you have to know this. So the way iterators work is they give you a way of being able to march through every element in a collection one at a time in some order. And in the case of a vector, it's usually from beginning to end. In things like trees or sets, the ordering may be more interesting. But in the case of a vector, it's very simple. So what an iterator does is it defines something called a cursor, which is just something that keeps track of how far along in the iterator, the iteration sequence, the iterator has progressed. And there's several different methods. There's a method that's called hasNext, which checks to see if there's anything left to be iterated over that hasn't already been seen. And then there's another method called next, which gives you back the next object that you're iterating over. So here, the hasNext method is going to check to see if the cursor, which would be initialized by the constructor of iter, or itr, whether or not this thing equals mCount or not. And mCount is actually the count of the number of elements in the vector. So you can see within this inner class, we're actually accessing a field defined in an outer class. And that's because it's a non-static inner class. We showed some earlier examples of anonymous inner classes, and this is not an anonymous inner class, but we'll talk more about those later. Here's the next method. You can see that next also accesses this count. Next in this case is checking to see whether or not, or assuming that it hasn't run off the end, it goes ahead and returns the element data at that location. So it'll give you the next element in the iterator that's being iterated over. So learning how to write iterators is something you'll have to know about because we'll do them as for the different assignments. Yeah?
So for the next method, you don't need to say throws or
Was that a statement or a question?
that's a question. You said that we had to specify that.
This is just, I'm just cutting and pasting code out of the Java release. So everything you're seeing here is what Java does. So what I think if I'm not mistaken, I think the question you're asking is, does next duplicate the check that hasNext does to see if it's reached the end? Is that the question that you're asking?
No, you said that method had like six parts before, and one of them was kind of like says what kind of errors it can throw.
So okay, so the point I made before about a method declaration, or definition actually, having 6 parts, that was about when you define a method, right? So you have return type or void, method name, list of parameters, exception specifier, body, etc. This is the implementation of a method. And this particular method is actually going to throw what's called an unchecked exception. And we'll talk a bit more about those later. So an unchecked exception actually does not have to occur in the signature of the method. So an unchecked exception would be something like, well, in this case, it would be out of range or index out of bounds or something like that. That doesn't have to be defined. Yeah?
Does a nested method, does it run when the code gets to it? Or does it call?
It has to be called. And keep in mind that when things are nested, it's usually as a convenience to group things together hierarchically. So as we'll see here, if you have a vector, then you have methods like element or element at, or I guess at element, index of. These are methods that work on the vector. And then there's also a method that every iterator has, which we'll see later, called iterator. So every collection has a way to get back an iterator. And when you call the iterator factory method, which we'll talk about a little bit later, it will give you back an instance of the nested class iter, but it comes out to you as an iterator object. And then, of course, you would call the methods to iterate through the things. And we'll see some examples of that a little bit later.
So is iterator an interface?
Iterator actually is an interface. Yes, iterator is an interface. And the reason we know it's an interface, how do we know it's an interface? Because we implement it, right? So if it was a class, we'd have to extend it. But in fact, just for kicks, I'll show you the iterator interface. It's kind of cool. In fact, well, you'll have to know how to do it if you're doing the grad version of the assignment. And for the undergrad, you'll have to do it for the next assignment. So let's see. Iterator interface Java. There we go. So as you can see, it's pretty simple. It's got three methods. It's got hasNext, which we just looked at. That checks to see if there's anything that hasn't been iterated over yet, which returns Boolean. hasNext, which returns the next element in the iteration. That's of type E, of course. And then remove, which is actually used to get rid of the element that it's currently iterating over in the collection, which might be implemented, might not. So yes, iterator is indeed an interface, and you'll get more practice using it shortly. Was there other question? Yeah?
Just trying to understand like the application of a nested class. Would that make sense in like maybe like a binary search tree with like the node being a nested?
Yeah, great example. So if you take a look at collections, so all the stuff we've been talking about here so far, vector, abstract map, stack, tree map, all those things, those are all examples of collections. And collections always have certain things that they are capable of doing. So every collection is capable of being iterated over. So every collection implementation will have a nested class which will implement iterator. It may not be called iter, but it doesn't really matter because you're never going to see it by its actual name. In fact, as you can see, this is actually a private class, right? This class is not accessible to anybody except somebody who accesses this through the factory method called iterator, which we'll talk about later. So all collections have nested classes. Split iterators are used for parallel streams. We'll see those examples later in the course. But the usual reason for having nested classes is to be able to encapsulate something, to hide it or nest it so that you can have a hierarchical understanding of things. And of course, that's why we had this, right? So the metaphor here is those little nested Russian dolls that nest inside of each other. I guess we need to put Putin here over on the left. Although the funny part is having a big Putin would be somewhat humorous because he's actually very short. So they actually should have put him, in the inside, make him the small guy. So those are inner classes. Then there's also static classes. They're also nested classes. So an example of a static class would be a split iterator. So vector split iterator, implement split iterator. We're not going to talk a lot about split iterators right now. You'll get more practice with this with assignment 2 if you're taking the grad part of the course. The main difference is that that static nested classes cannot access the non-static fields or methods. They can only access static fields and methods. So they've got a slightly different relationship. And you'll see this causes no end of complication later in the course when we get further along. All right, so here are some things that you ought to be able to do. This is a good quiz fodder. So, how do you compare and contrast abstract classes versus interfaces? What's the similarities? What are the differences, right? So, abstract classes have some things in common with interfaces. For example, you can't instantiate an abstract class just like you can't instantiate an interface. You may contain a mix of methods declared with or without an implementation. Interfaces can have implementations, which are called default implementations. Static classes or abstract classes can have implementations, just like we saw here. So those are some things that they have that are in common. However, there's a bunch of things you can have in an abstract class that you can't have in an interface. So if you think about the example we showed before where we have the big muscular class and the skinny, scrawny interface, the basic idea there is that classes, even abstract classes, have more heft to them than interfaces. So abstract classes can define fields that are not static and final. They can define public, protected, and private concrete methods. So here are a bunch of things that you can put into an abstract class. Like you can have a protected method, a private method. You can have various kinds of fields and so on and so forth. These are all things you can put into an abstract class that you could not put if this was purely an interface. With interfaces, all the fields are automatically public, static, and final, and all methods are public. So here are some examples that we looked at before, like comparator. You have some methods here. These are all public. You can't make them non-public. That wouldn't make any sense to have a non-public interface method. Here's another important difference. So with Java, not C++, but with Java, an abstract, a class can inherit from one other class. It can extend one other class, which might be an abstract class or not. But the point is you can only have one class that you inherit from, or you extend, as they say in Java. In contrast, you can implement as many interfaces as are necessary. And in fact, when you take a look, if you were so inclined to take a look at the Java collections framework, you will see lots and lots of stuff that looks quite a bit like this. There'll be one class that's extended, and then a whole pile of interfaces that are implemented. In fact, if you're being a bit uncharitable to Java, their collections framework is quite a bit of a hodgepodge and reflects sort of organic growth over time where they just kept throwing all kinds of weird, wacky things in there. And the interfaces are pretty fat and complicated. But there's also some cool stuff there as well. Yeah?
What happens if you're implementing methods with the same name?
You'd have to disambiguate them in the subclass. You'd have to define the method implementation.
Is that like a major advantage of interfaces, or is it just like not?
The major advantage of interface is it just tells you a set of signatures, doesn't give you any implementation constraints. It gives you interface guidance, if you will, because it says what fields are valid. And interfaces can then, you can mix and match them in multiple inheritance or multiple implementation, I guess is a better term, in any way you deem fit. All right, so now I think we're going to talk about packages and importing classes and so on. So you can refer to any class that's in the same package by its name. So here's an example, Java util. As we talked about before, that's a package. You can define a package by saying what the package name is at the top. And you could have lots and lots of files that are all part of the same package. In fact, everything in the java/util/directory, or folder, is in the Java util package. So here's an example where we have two classes, arrays and vector, that are both in the Java util package. And as a result, they can call each other's methods. So if you take a look here, the arrays class defines the copy of method, and the vector class can use arrays.copyof directly without having to do any further disambiguation. And if you do that, then the Java compiler says, aha, I'm going to look for a class called arrays inside of the current package, which is Java util. If you have things that are not in the same package, however, you have a couple of choices as far as how you refer to them. And this is kind of nitty-gritty, boring, but if you don't understand it, you'll be flummoxed at times. So I'll go over it quickly. One way to refer to things, if you're in a different package, so here's the Java util concurrent package, which is not the same as the Java util package. So in the Java util concurrent package, if we want to refer to abstract map, I can either explicitly qualify it with a fully qualified name, java.util.abstractmap, which is rather verbose. And it actually somewhat frowned upon as being a little bit too verbose. That's one way to do it. The other way to do it is to import that particular class from that package. So now I can just say, instead of saying Java util abstract map, I can just say abstract map because I've imported it. Now, you can either import things one at a time, like Java util abstract map, Java util vector, Java util hash map, Java util this, Java util that, or you can just say import java.util.star. And that just dumps everything in that package into the namespace that's available to be accessed in a non-fully qualified way. So that's a little bit more succinct. Do you ever stop to ask yourself the question, why is the word parsimonious so long? You should think about that. Never made any sense. So here's an example where we typically have a list of imports at the top, or not at the top, but right underneath the name of the package. You'll list all the files you want to import. There's lots of ways to create classes. You can use Eclipse. You can go in, if you're using Eclipse, there's ways of creating a new class, and you can fill out some of the properties and hit a button, and then it'll create the class for you. Likewise, you can use your favorite text editor like Emacs or VI or whatever you like to use, and you can create your files that way. With Eclipse, it's really quite easy. As long as something shows up in a directory that's part of the Eclipse project, then Eclipse says, aha, that must be a file that's being used by this project, and it'll go ahead and try to compile it and import it into the project, or include it in the project. So there's lots of different ways you can do that. All right. Any questions about any of this stuff? We're making good time here. Next thing I want to talk about is Java strings. I'm not going to spend a lot of time on these, but you've got to know enough about Java strings because they're used all over the place in Java. And even though it's somewhat mundane, you'll have to know at least what I show you here. So strings are kind of interesting. They're different in Java than they are in some other languages, and they're kind of treated in a bit of a special way. So here's an example of two strings, string 1 and string 2, both of which reference the same string literal. And Java does some rather clever things with its bytecode format and its class representation. And it basically merges all the string literals together into a constant pool, as it's called. And so these things will actually both reference exactly the same string object. What's interesting about this, or one reason this works, is because strings are immutable. You can't modify them once you've created them. Here's an example of how you can print stuff out. So here we print the string literal to the output, A, B, C, D. Here's a case where we make a string that points to that literal, and we print the string, and that gets printed out. You can also do some other things to strings. Keep in mind, strings are always immutable. So when you do operations on them, they create new strings. Here's an example where we have one string with CDE, and we go ahead and print the string literal, ABC, and we basically concatenate CDE to the end of it, so that prints ABC, CDE. Here's a case where we go to the string literal ABC, and we go ahead and we extract out a substring starting at the beginning and going up to but not including the second item. And this will not modify this string, because of course it's a string literal. It'll create a new string that has those values. So strings are constants. Once you set them, you can't change them. So here's a funky example where we have string CDE, and as you recall, CDE had CDE, and we want to replace C with D. And so when we say CDE.replace C with D, that doesn't modify CDE. It creates a new string called D. It should be called DDE. And it goes ahead and makes basically a copy of CDE replacing C with D. And you can find out why strings are immutable in Java. There's a bunch of optimizations you can do. It makes certain things a little easier to optimize. It has other nice properties about eliminating bugs and so on. Another little thing you got to know, just because it'll bite you if you're not aware of it. As a general rule of thumb, don't use the equality operator to check whether two strings are equal. Instead, use the equals operator. And here's a good example that illustrates how those differ. So we have string A, which has got the characters FOO for foo. And we have string B, which is just the null string, or a string with no elements in it. And then we say B, which is null, concat foo. So that's going to create a new string C. And that new string C, of course, is foo, right? Just like string A. But if I say A equals C, this will actually fail because they're not pointing to the same strings in memory. They don't point to the same objects. However, if I say A equals C, then those will, in fact, compare correctly because they'll compare each element in the strings by their values, their contents, not by comparing their references. Yeah?
Does the equals method come from another interface too?
Yes, it's inherited from object, which is the root of everything in Java. We'll talk about that in a minute. Okay, next topic, and we're doing quite nicely here. Question?
You just said A equals foo and Z also equals foo, and then equals equals.
Yeah, that would actually work because of the fact that they do constant pool optimizations.
And it's only because of concatenation that doesn't work.
It's only because we're creating a new object that references a new thing altogether. Yes, that's a very good observation. Yeah.
Why does it refer to a new thing altogether?
What is it? What?
Why does it refer to a new thing altogether?
Oh, just because it's creating a new object. Remember, the way things work, if you do like operations on a string, it makes a new string. So it's making a new string. So you're getting back an object to a new string that just happens to have the characters FOO in it, but it's a new object.
Is there a string constructor? So like string.
Oh yeah, there's definitely a string constructor, sure. Yeah, well, I mean, all these things up here, this is a string constructor right there. That's making a string out of a string literal. You could, if you wanted to, although it's redundant, say string A equal new string less than, or left paren foo close paren. But that's redundant. You don't have to do that. Yeah.
If you had done just b concat foo without setting it to another variable, does it modify b?
No. Going back to, so the question is, does it modify things? Strings are constant and can't be changed once they're initialized. So anytime you do an operation that appears to be mutative on a string, it's actually doing that operation and returning you a whole new string altogether.
So you would have to go like CDE equals CDE dot replace.
Yes,
And that would change
that
your variable.
would do it. Well, you're never going to change the variable. You're only going to make a
change the.
you're going to make you'll make a new one that has the things replaced. So here's an example. D is a new string that contains the contents of CDE where C is replaced with D. But CDE is not changed.
If you wanted to modify CDE,
You couldn't modify it.
you can't do CDE equals CDE dot replace.
Oh, yeah. Yes, but that'll create a new object and assign CDE to the new object. Yes, yeah, good point.
On the next slide, if you made a string d equal foo, could you do equal equals to A or to C?
Yeah, so keep in mind that Java does this constant pool optimization stuff that we show here. So string literals always get resolved to the same place.
There are two different ones, so would it be compared to A or?
Well, they would actually all be pointing to the same thing. If we said string A equal foo, string B equal the string foo, string C equal string foo, then they would all be pointing to the same thing.
If you made string d equals foo, it would be equal equals to A, but not to C.
Well, C is not doesn't have a character literal. It has a new object that took the null string and concatenated foo to it. So that's just a whole new object altogether. But if you directly assign foo, then it's going to have the constant pool memory reference for each of those things stored there. And so it'll just go and resolve to that. Other questions? All right. So exception handling. So you'll need to know a bit about this in order to be able to do the assignment, and we'll also talk about different kinds of exceptions. So as we talked about before, when something goes wrong in a Java program and you want to let people know, you use exceptions. Now, prior to having exceptions, most languages dealt with error handling by having return values. So if you ever a program in C, which does not support exceptions, if something goes wrong, like you read from a file that's not existent, then you get back a special error code, like a -1, and some other value will get set and say, oh, that's because the file didn't exist, or whatever. But the problem with error code ways of reporting errors is it's easy to ignore them because nothing forces you to deal with them. In contrast, exceptions cannot be ignored. So if something goes wrong, then an exception can be thrown to notify the caller of the error. So here's an example. So any code can throw an exception by using throw. So here's our vector. This is the vector constructor. If someone gives a value that's less than 0, then we're going to throw an illegal argument exception. Notice, by the way, that there is no specification saying illegal argument exception for this. This is what's called an unchecked exception. It's a runtime exception. So if you give -1 or lower, illegal argument exception is thrown. Likewise, here's the last index of method, which is going to go ahead and try to find the last index in this object. It's going to go search for this object starting at this index. It's going to find the last one. Well, if you give it an index that's beyond the end of the array, this guy's going to throw an index out of bounds exception. So these are examples of throwing exceptions which indicate errors have occurred. And now we'll talk about how you handle them. But before we do, any questions about throwing an exception? Notice, by the way, you always throw a new exception. So, or you have to throw an object that's been allocated by new. So you, unlike, this is a little bit different from C++, but you throw a new instance of one of these objects. And these by the way, are just good old object or classes. They're nothing special. So when an exception is thrown, it causes the normal program execution to stop. So let's assume that we had a bunch of methods calling each other. So method A was called first, it called method B, it called method C called method D, and method D throws this exception. The second throw occurs, like one of these things occur, the control flow at that point leaves the method and starts going back up the call chain looking for an exception handler that knows how to handle that exception. And we'll talk about, there's some subtleties in there, but that's the basic idea. So you can think of exception handling as basically sort of a go-to statement in some sense that can potentially go much further away than the context, the scope in which the problem occurred. And we'll talk more about that later. So it searches up, the Java runtime searches up the call chain to try to find an exception handler. Once it finds one, so for example, in this case, this is where the exception handler was, control is then transferred from the point where the call threw the exception to the place where the catch occurs. And that's kind of why it's like a go-to, if you will. So control is transferred, and various things happen along the way. And Java semantics are slightly different than C++ semantics here, but we'll talk about how that all works in just a minute. All right, so how does this whole thing work? Well, much like C++, when you want to indicate a region of code where exceptions might occur, you surround them with what's called a try block. So here's an example where we can say, here's some class we developed. My class has constructor, and we go ahead and we have a try block. And as you can see here, we're going to try to make a vector with a -1 as its size, which is not going to be very happy. And we're also down here, we're going to try to have a vector that has one element in it, and then we're going to go ahead and search starting 1 past the end. So that's not going to work either. So both of these things are regions of code over which exceptions might occur. Now, in this particular case, I just have one thing happening inside the try block just to keep it on the page. In reality, you can have many, many, many statements inside the try block. So a try block is just a region of code where things might go awry. Now, when you have a try block, you could also have one or more catch blocks. And of course, if exceptions occur, then the first place control will transfer to see if we get a match is the catch block. So in this particular case, we have a vector. We try to create that. That's going to end up throwing the illegal argument exception. And in this particular case, we're going to catch it right there, right where it happened, or close to where it happened, and do something about it. Maybe we report an error, or print a stack trace, or retry, or do something, right? And the same thing happens down here. We're going to catch the index out of bounds exception. So you can have one or more catch blocks. And I'll show you examples of more than one catch block in a second. You can also have, associated with a try block, which may also have catches, you can also have what's called a finally block. And the finally block always runs when the try block exits. So after the try block is finished, you can then go ahead and have a finally block which will get called. And that's the last thing that gets done before that whole block of code returns. And a common thing you do in a try block is, or in a finally block, in a try finally block, is you go ahead and do stuff that you always want to have run no matter how you get out of the try block. So here's a simple example. We'll talk more about this later in class. We acquire a lock. We do some stuff that might throw an exception. And irrespective of whether an exception is thrown or not, we want to unlock that lock before we return control. So finally always gets run. It's kind of a catch-all to do things that need to be cleaned up no matter what. Now, if we were in C++, we wouldn't use finally blocks. Instead, we would use destructors. And they have somewhat the same flavor as a finally block. It's a little different. Destructors work on objects, whereas finally blocks work on statements. Another interesting thing, this came with Java 7, is a try with resources block. And it's a try block that declares one or more resources that have to be closed after the block exits. And this is actually super cool, and I'll use it a lot in my examples, so you need to understand vaguely what it does. So what happens here is the following. This is kind of funky syntax, but this is a method called read first line from file, and we give it a path name of the file. And it comes in here and it says try, and then it has basically the try with resources portion. It goes ahead and it opens up the file, makes a new file reader, makes a new buffered reader, and assigns this buffered reader to a variable called buffReader. The scope of this variable is only inside of the try catch block, or return try finally block. And so inside the body of this thing, we can then go ahead and read a line from the buffered reader, and that's what gets returned here, a string from that. And then when we hit the end of this try block, this try with resources block, it automatically calls the close method on this object and cleans it up. So this is what's called auto-closable. And it's cool because it's kind of like destructors, but not quite, and it makes it so you don't have to write really ugly, torturous code. So if you want to learn more about this, go take a look at the try resource close link I have here, and it'll explain and give you some examples and show why it's an improvement upon what was there before. All right, now we're going to now that I've talked about try blocks, catch blocks, finally blocks, and try with resources blocks, now we can talk a little bit about exceptions and how they're specified and so on. So if you want to force people to deal with an exception on a method, you specify a catch, a throws clause, or an exception specification list. And this says that any caller has got to provide an exception handler for this. And these are called checked exceptions. So here's an example of how we use this. You come into this method, and we try to write the object from the vector using writeObject, and you've got to catch the IO exception. If you don't put that in there, your code will not compile. It'll yell at you and say something along the lines of, have to implement the IO exception here, and you have to. So that's basically what you have to do. Now, you can also have different catch blocks for different kinds of exceptions. So here's a sort of a stripped down case that leaves out most of the interesting details. We have a try block that does some stuff, and let's say it's working with vectors. And there are a bunch of different kinds of things that could go wrong. So you can put an ordered list of catch blocks here, and so if any exception occurs, it will then search in order that you list it here to try to see the first one that matches. So it'll first check to see if it's an index out of bounds exception, and it'll then check to see if it's an illegal argument exception, and so on and so forth. If it reaches the end of these blocks and it hasn't got a match, does anybody know what happens with an exception? If you reach the end, what'll happen?
It's passed up to the previous number.
Right. It'll get passed up the activation record stack, the call stack. So whoever called this method, whoever called a method, then wherever that call was made, then it'll start looking there to see if there's any catch blocks that match. And if it doesn't find them there, it'll look up at the next level in the call chain. And this propagates up and up and up and up until finally either it finds something that matches or it falls off the end of the thread that was running the call chain, in which case an unhandled exception handler can be defined to deal with that. Here's another example. And this is kind of what I was just talking about. So here's a method called bMethod that calls a method. If these exception handlers don't match, then this call will return here, and it'll check to see whether it matches IO exception. And if it doesn't, it'll propagate it up the call chain there as well. Now, if you really want to catch every possible exception, then you can catch something called exception. And exception is the base class of all exceptions in Java. So just like object, class object is the root of all inheritance hierarchies in Java, so too is exception the root of all exceptions in Java. And so this is how you can catch all exceptions. Believe it or not, there's actually something that's even more catch-all than exception called throwable. So every runtime error will be caught if you catch throwable. And I'll let you read the description on the web to explain the difference between exceptions and every runtime error and so on. Usually you wouldn't do this kind of stuff unless you were writing very low-level systems code, because it's unusual to have to catch every exception or every error. But if you need to, you can do it. The main thing to keep in mind with exception handling is if there isn't much you can do about something, you might just want to let it propagate up the call stack till somebody who does know how to deal with it can figure out what to do. And this is one of the annoying things about exceptions. We'll talk more about this as we go through examples. Here's how you can take an exception and wrap a runtime exception around it. So here's a case where we have exception E, and we're going to wrap a runtime exception and then throw a new runtime exception. So that's how you can throw things out of methods that otherwise wouldn't let you throw the exception because it wasn't listed in its list of throwables. So again, these are sort of esoteric issues, but you need to at least have some vague understanding of them.